Over the past 2 decades, observational social science has relied heavily on a single statistical workhorse, difference in differences, or DID. It is designed to compress millions of chaotic data points into a single, understandable metric of cause and effect. The field has recently solved several complex problems within this framework. Researchers have developed robust methods to handle staggered treatment timing, ensuring that groups entering a study at different times don't bias the result. The toolkit is now an incredibly sophisticated, featuring synthetic controls and new imputation techniques and rigorous sensitivity analyses to detect when the core assumptions of the model begin to fail. We have reached a point of remarkable mathematical precision, but this precision introduces a distinct vulnerability. If the mathematical object we are estimating is the wrong target for the problem, our equations will yield highly precise, completely misleading answers. This vulnerability stems from what we might call an experimental ontology. Because observational data is messy, social scientists adopted the logic of randomized controlled trials to make sense of it. Within this framework, a cause is strictly defined as the expected difference in potential outcomes. Causation is conceptually locked into a single metric, the average response of a population to a discrete intervention. For a discrete intervention, like a targeted minimum wage hike or a localized tax credit, the average response is a useful metric. But historical processes like revolutions, wars, or famines do not function as simple treatments administered to a stable system. Instead, these events reorganize the system itself. They trigger highly divergent, path-dependent trajectories, where similar groups experience completely different outcomes, often branching off into survival or collapse. When we compress these divergent trajectories into a single representative coefficient, we are choosing to ignore the dispersion of those paths. Averages, by definition, smooth over the most extreme differences. By focusing so intently on identifying the average effect, we have made the mean the only rigorous object of study. This ultimately raises a very fundamental question. What happens to our understanding of history when the most important data exists in the extremes that the average can't see? To answer that, we have to look at the formal mathematical incompleteness of the average treatment effect on the treated, the ATT. In process A, the population shifts uniformly right by 5 points. The math reads an average effect of 5. In process B, a small fraction suffers a catastrophe, stretching a long tail to the extreme right, yet the calculated average remains exactly 5. Every robust DID estimator returns the exact same coefficient for both scenarios. The mathematical formula is entirely silent on the profound structural difference between a uniform societal shift and a total catastrophic divergence. The estimator registers this chaos only by widening the standard error. It treats extreme tail data as noise that makes the mean harder to pin down. Researchers often interpret this widened error margin as a mere statistical nuisance to be corrected, overlooking the glaring signal that the population is splitting into two totally different realities. We need a different conceptual model, variance-altering causation. Here, the widening gap between survivors and casualties is the primary causal effect. An estimator is only a success if it actually measures the right thing. When an event creates divergence, the average is the least informative number we can compute. We can test this against high-stakes empirical data from the Chinese Great Famine, analyzing county-level mortality rates between 1954 and 1966.
Our baseline factor is the strength of local genealogy networks, which serve as a proxy for social capital and the community's capacity for mutual aid. Using a factorial DID setup, researchers measured how social capital moderated the famine's mortality impact. Did these kinship ties actually save lives during the peak of the crisis? The entire distribution of mortality across these counties. It was a massive variance-generating event. This reveals the reality hidden by the mean. Social capital prevented a massive bifurcation of counties into catastrophic trajectories. The primary historical interest here is whether social capital prevented local populations from collapsing entirely. Treating the famine as a uniform shift misinterprets the event. It was a process of divergence, revealing the massive gap between endurance and total annihilation. rotating the data to 1960 reveals the physical shape of this divergence. The modal county fared similarly across both groups, clustering on the left. But catastrophic divergence happens in the right tail, where low genealogy counties extend past 100 deaths per thousand. That moderation coefficient of -2.9 is mathematically accurate, but it misses that the actual loss of life concentrated almost entirely in this extreme tail. The danger of the average is clearer when looking at ethnic minority status, which tracks a region's exposure to strict state extraction and ethnic hierarchy. Minority status barely moved the average mortality shift. The peaks of the two curves overlap almost perfectly, yet it massively inflated catastrophic tail risk, doubling the chance a county would exceed 100 deaths per thousand. A statistical method built strictly to recover average effects will systematically underweight factors that operate purely through the extreme tail. By optimizing our analysis for the mean, we are effectively choosing to look away from the most vulnerable populations. This critique directly impacts how we evaluate policy. We can see this through the policy analyst's decision problem. Imagine a choice between two policies. Intervention A uniformly reduces mortality by 3 units for everyone. Intervention B leaves the average completely unchanged, but it compresses the risk of catastrophic failure from 10% down to 2%. The standard difference in differences framework guides policymakers to favor intervention A simply because it produces a larger mean coefficient. To favor intervention B, the analyst must use a distribution-sensitive calculation, one where the penalty for extreme regional failure outweighs minor average gains across the board. Evaluating policies for crises like famines or pandemics using a mean-based loss function is a massive, unacknowledged normative choice. It treats a slight improvement for the many as equivalent to preventing total ruin for the few. To improve evaluations, social science must routinely report variance and tail effects, actively designing models to capture these outliers. Methodological success shapes the boundaries of what we are allowed to see. If we continue to measure only the average, we will only build policies for the average, leaving the most extreme human experiences in the dark.